Okay. In this video, I am going to correct a mistake that I made in the class. So, and also in a question in your first spot test. So there it was said like that the deflecting torque in any instrument does not depend on theta, or is not a function of theta. That is what I told, but I should rather rectify myself and say, by striking out this, does not sorry, I should rather say need not depend on theta, or in other words, is not necessarily dependent on theta. So why is that so? Let me explain. Let me consider first PMMC instrument that we studied first, where we had circular pole shoes and a circular core, so that the flux density is flux is radially inwards, and the density of flux on the periphery is constant and equal to B. And in this case, if this is my coil, no matter at what, so this is my coil, no matter at what angle this is, at what theta it is, the flux density which is in the direction of the coil at this point is always B, no matter whether it's here or here, or like this or like this. And in this case, in this ideal scenario, we found the torque Td to be equal to B times L, length of the coil, the diameter of the coil, number of turns, times I. And we also mentioned that if in another extreme ideal case where we have the flux density to be parallel and like this, and in that case, if the coil is like this at any point, so there the torque Td is equal to this BLD in I cos theta, where theta is the angle from this line. So in this case, deflecting torque is a function of theta. Okay, but ideally we don't prefer this scheme compared to this. This is because in this case the deflection, so we also saw that that at equilibrium k theta, which is the controlling torque, is equal to Td. In this case, this is equal to some constant times I, and therefore the deflection is proportional to the current. So the scale of this meter will be linear, whereas in this case, in the second case, k theta equals Td equals some constant times I times cos theta, and therefore current and the deflections, they are not proportional. So here the scale won't be linear or uniform. So we ideally don't like this, we ideally like this, and therefore we want the deflecting torque not to be a function of theta, but anyway, I mean, this is an ideal situation. The flux density might not be exactly uniform and can in practice be a function of theta, strictly speaking. Let's consider, say, now electrodynamic instrument. So Now let's consider again an ideal case where we have this is my field coil, and so therefore the flux is like this. So they are parallel, perpendicular to the field coil, and the circulate and come back, something like this and this. And say inside it I have the second coil, which is the moving coil, and then the flux linkage of so if the flux density for generated by the field coil is B, if the area of the second coil is so B is flux density, let A be the moving coil area, and therefore the flux linkage so the flux linkage is proportional to B times the projected area of this coil, so which is proportional to BA cos theta, where theta is the angle, this angle. So here it's it has maximum flux linkage, and as theta increases, flux linkage decreases. And then we also saw that the torque in electromagnetic device is TD is proportional to dm theta. What is dm theta? It is the rate of change of mutual inductance as a function of theta. Now, since we saw that for a given flux, say this B flux is generated by a current of I in the field coil, so that means in this case M is proportional to the flux linkage phi divided by the current in the other coil. So M is equal to the flux linkage of the second coil due to the current in the first coil. And then since phi is VA cos theta, so this is proportional to again cos theta by I, and therefore dm d theta is proportional to sin theta and is again a function of theta. So the torque is also a function of theta. So even in this case, if the situation is something like this, this is an ideal case, we see that flux linkage is the deflecting torque is a function of theta. So so essentially what I meant to say that the deflecting torque need not be a function of theta, but I cannot say it is never a function of theta. Next, let us consider now the third type of instrument that we discussed, that is moving iron instrument. And let's for example consider one particular construction of moving iron instrument, which is a repulsion type instrument. So we have a coil like this. So we are looking from the top of the coil. So these are the two terminals of the coil, and inside this I have a spindle, an axis from which I have a piece of iron bar, so which is vertical to this paper, and then there is another piece of iron bar which is rigidly attached to the coil. So this cannot move, but this one can move, and the indicator is connected to this axis or spindle. And then we saw that that the force of repulsion between these two is proportional to the amount of magnetization of these two iron bars, which in turn depends on the magnetizing current. So both of them get magnetized in proportional to the magnetization current, and therefore we said the repulsion force between them is proportional to I square. What I didn't mention or what I didn't consider is that this is not only proportional to I square or the strength of magnetization, but this is also inversely proportional to the distance between these two bars. So which for that I should put an 1 by r square, where r square is the distance between these two bars. So deflecting torque in this case Td is proportional to this. And then this r square is a function of theta. So basically, when theta changes, as the angle changes, this r changes, and therefore this is again a function of theta. So there are other constructions which is there in our book. So where I'll just briefly mention here, where we have tapered cylindrical piece of iron which is fixed, and on top of it a movable iron bar is there which moves as they get magnetized. So for example, if it is magnetized like this, N, S, 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 and this bar is also magnetized like N and S, then they repel, and then this bar is forced to move rightwards. So this construction can be argued to have deflecting torque which is less dependent on the position of the bar. So ideally we want the deflecting torque to be not a function of theta, but yes, they can be function of theta. Thanks.